Hi, and welcome back to Allen High School's discussion of the structure and function of pure substances, followed by a discussion of mixtures. Now, in our next segment here, we're talking about structural integrity. And for network covalent, it really varies. But when you have network covalent, you have fixed bond angles. Those fixed bond angles make network covalence typically very hard. Now, diamond, you should know, is very hard and inflexible. And here's the structure of diamond here. You see around each carbon, we have an sp3, and there would be a fixed 109.5 degrees around each. And diamonds are very hard. The size is going to be, dependent on when you can fracture that diamond, and that's often dependent on where there's a structural imperfection in that. Glass is hard, but readily breakable. Again, depending on the glass, and people tend to dope the glass with different additives to alter its properties. Now, graphite's a little different. Graphite is stacked in layers like this, and the attraction between the layers is London dispersion. And so graphite can actually be a little bit slippery, because those layers can slide or have movement on top of one another. Metals, if we talk about some of their structural integrity, remember that sea of electrons shields the positive charges from sensing one another. So it keeps the ions from attracting one another. So metals are very malleable, because if you shift the structure, so let's say you've got these positive ions, if you shift this one way and this the other way, you have that sea of electrons in between that provides that shielding effect, that no matter what way you pound that out, they're not going to repel one another. And so metals tend to be malleable and ductile. Now, some metals are actually rather soft. If they would let me buy group 1 metals, you'd see that they're soft. You can actually cut them with a butter knife. And others are very, very hard, difficult to cut with wire cutters. Malleable describes the ability to pound into a shape. Ductile means the ability to stretch into wires. And so you should know the difference between those two terms. Okay. Now, ionic, in terms of structural integrity, they tend to be brittle. Ions are held in a rigid lattice. Ionic compounds have, and I printed the wrong copy here. I don't have my little lines filled in. But ionic compounds have little flexibility. People that have little flexibility tend to, if there's a lot of stress in their life, they tend to fracture. And that's what happens here. They tend to fracture when a stress is applied to them. And here's a good picture of this. You notice that they are in this alternating positive-negative. If you give it a sharp blow, what happens is that positives end up being by positives, negative ions by negative ions, and that causes repulsion, which pushes layers away from each other, and it's going to fracture or crack. Okay, and this website is a really nice little animation that shows the difference between metals and non-metals, metals and ionics in terms of their structural abilities. Covalents tend to vary. They're found as gases. We've got hydrogen, we've got methane gas, we've got all sorts of different things. We've got liquids at room temperature, water, we've got solids at room temperature. Iodine happens to be a solid. If you get very long hydrocarbon chains, like let me just be really, octane, C8H18. Okay, that's going to be a liquid at room temperature. So they're really all over the place. It depends upon their polarity and their size. In this case, and I know you can't see that 8 very well, so let me rewrite that for you. We've got C8H18. In terms of the polarity, it's nonpolar, but because of its large size, it has a significant London dispersion attractive force to it. So it's a liquid. So they're really all over the place, but they're neither brittle nor malleable nor ductile. Okay, is kind of what their structures are. But you should be able to justify for each of these why a network covalent is a solid at room temperature because of those strong covalent bonds, why a metal and ionic are all solid at room temperatures, and then be able to begin to justify, and this is what we're working towards, when covalents would be solids, liquids, or gases, and to justify their states at room temperature. Okay, now this next we're going to start getting into some of the other properties of ionics and covalents, and so I want to just do this quick summary table for us, and it's based a little bit on some of your pre-AP knowledge, but I'm going to be going over most of it. I'm not going to be leaving you drifting. Now, this assumes the same size. So if we're talking about the same size molecule, London dispersion is the weakest. And let's see if we can make those arrows a little bigger. Whoa, didn't mean to do that one. Okay, let's get those out of our way. London dispersion tends to be the weakest, and your ionics, your metallics, your network covalent are the strongest. We're not going to make a huge distinction between them because there's such a huge overlap amongst them. So these are the strongest, and these are the weakest. Again, assuming same size. We got to compare apples to apples. Now, because of the attraction forces that we're going to be breaking, the melting points are going to go in this direction, lowest to highest. Boiling points go right along with our melting points from low to high. And this is a summary chart that's going to give you a reference point as we're continuing our discussion. The energy required to melt or boil, that's what our delta H of vaporization and fusion are. That's the kilojoules required to melt and to boil. It's going to take less energy, and it's going to take the most for ionic, the least for London, the most for ionic metallics and network covalents. Surface tension is something we skirt around in pre-AP. We want to talk about that some more. And we're going to talk about it a little bit more in terms of our molecular. So I'm just going to stop my arrow right there. If it hydrogen bonds, it's going to tend to have a high surface tension. For London dispersion, again, assuming same size, it's going to have a low surface tension. Volatility, if you remember, and if you don't, I'm going to come back to it. Volatility is the ease with which it goes to the gas phase. And I just drew my arrow wrong. I was getting a little carried away with my arrows there. This actually goes in the opposite direction. The weaker it is, the more volatile it tends to be. So these are very volatile, assuming same size. Water is not considered very volatile. Water does not go to the vapor phase very readily. And because of that, water's not going to have much vapor present at a given temperature. So it's going to have a low pressure for its vapor, whereas more volatile substances that go to the gas phase readily will have a lot of gas molecules and go to the high. Now, we're going to revisit all of these, but I wanted you to see this summary chart in terms of the intermolecular forces. So, what do we do if they're not the same size? Wow, you have got to, in fact, let me get rid of that. You have to memorize this phrase. This is the answer to so many of life's questions. All right, if you increase size, increase electron density, increase polarizability, increase temporary dipole moment, increase London dispersion strength. I'm going to have us all say that together many times. And if somebody out there is really creative, kiddos, let's make a video and post it on YouTube. Maybe we'll get some fun hits. So until our next time, this is signing off.